forget to start it. So everybody, recording is now on. Zach, we can't hear you, but you are muted. So you can unmute yourself, or I can unmute you.
Oh, is that better?
Yeah, now
Yep.
I can hear you.
Okay, cool.
You can also hit the video button so we can see you.
No webcam.
No webcam. Ah.
Well, just for the information, I'm targeting for about 30 minutes, a bit more, as we discussed, Jonathan. We will be a small group, so we can make this totally interactive. If you have anything to ask or any remarks, just shoot in the meantime as well. We can have a little discussion afterwards as well, of course.
Sounds good. So how'd you get into all this? Are you from the chip design area or from the software area? Where'd you come in from?
I'm from the software side. So the idea was totally that I'm a software developer and I want to have something as a software developer, and I want my software developers buddies to also have something that allows them to basically create hardware if there is a performance benefit to that. And this is behind a lot of design decisions in Hastlayer as well. But you will also show, and that's one of the things that that also makes it different from other similar systems, because we had software developers in mind first, not hardware designers.
Gotcha. All right. Well, let's go ahead and get started then. I think it's just gonna be us.
All right, that's no problem. Let me quickly start what needs to be started here. And I will also share my screen. So, all right, let me know when you can see my screen. Can you see my screen?
It says loading.
Loading, okay.
Yeah, I can see it.
Okay, great.
There it is.
Will this font size be okay for you?
Yep.
Yeah, it's readable.
Okay, fantastic. And then let's also start. Yeah. Okay, let's start. Then, hello again, everyone. I'm Zoltan Lewski from a company called Lombik, and what I would like to show you here is how to turn your, well, .NET software, spoiler alert, into computer chips, so basically logic hardware, with our tool called Hastlayer. By the way, that's interesting. By the way, everything that I will show you here is also up on GitHub. So if you didn't see some piece of code in detail, don't worry, you'll be able to check it out. I will show you the link later. Now, a little bit of interaction before anything else. As mentioned, I'm from a company called Lombik Technologies. We are based in Budapest, Hungary, in Europe. And actually, day-to-day, we are doing ASP.NET web development. Specifically, we are using a web content management system called Orchard. Now, if you work in the web sphere and you are a .NET developer and you haven't heard of Orchard, I really encourage you to check it out, because it's a very nice open source CMS. It was started by Microsoft, but now it's completely community driven and contributed to by companies like Lombik. And although we are in Hungary, actually all of our clients are foreign, and most of them from North America. And our customers even include like Microsoft itself, and Microsoft is also using Orchard, or the Smithsonian Institution, or the .NET Foundation. But when we are not doing some Orchard development, then we are doing some research and development, like for our Hastlayer project. And actually the inspiration of Hastlayer comes from my university time. A few years ago, when I was studying to become a software engineering and computer science major, we also had some hardware design classes. They were called digital system labs. And during those labs, we indeed had to design little pieces of logic hardware, even small CPUs. And that was very cumbersome. All the tooling was very inconvenient to use. And the whole paradigm of hardware design was very alien for us, who all of us came from some software developer background, or at least we have done some programming on the university, because hardware design is really different. And at the time, I had the idea that there should really be a way to do this in C#. Well, there was no way to do that, but there is now with Hastlayer, so let's see. Just a word of warning, Hastlayer is pretty much in an alpha stage. So it works fairly well. It has some nice results, as you will also see, but it's not production level yet, production ready yet. Why this is the case and what we are doing to mitigate that, I will show you later. Okay, so what on earth is Hastlayer? Well, Hastlayer is a tool that takes a computer program and converts it into a computer chip. So we can also say a piece of logic hardware. We can also say that Hastlayer takes a piece of logic which is expressed in software form and creates an equivalent logic which is expressed as hardware form. So the logic stays the same, the algorithm stays the same, but it computes, the results stay the same, but before we had a piece of software and now we have a piece of hardware. And all of this happens with some flexible devices called FPGAs. Have any of you worked with FPGAs before?
Yeah.
Zach, you have. That's cool. Nobody else, it seems. Are you more from the software background or more from the hardware background?
Hardware.
Hardware. Okay, then it's no surprise. Then this will be the other side for you then, because with Hastlayer we are coming from a software developer background. For all the others, FPGAs or field programmable gate arrays are pretty much computer chips that can behave like any other computer chip, within limitations, of course. So we can also say that FPGAs can be dynamically rewired to mimic some piece of hardware logic. So for example, if you want to implement an old Intel CPU, you can use an FPGA to do that. Or if you want to have a computer vision processor, you can use an FPGA to do that as well. So for all of you who haven't used FPGAs before, or haven't worked with FPGAs before, that's not the same thing, most possibly still have used them in some indirect way even. For example, if you Google something on Bing, so to say, then you have already used FPGAs, because Bing, as of a few years ago, is accelerated by FPGAs. Microsoft Azure also has FPGAs. They are not yet publicly available, just handle some networking tasks. But FPGAs can also sometimes be found in household appliances like routers. Or if you went to a doctor and got an X-ray or a PET or an MRI scan, those machines sometimes have FPGAs as well. And autonomous vehicles are not without FPGAs either, because sometimes they use FPGAs for some computing tasks, like computer vision even.
Now, didn't someone recently do a cloud-based FPGA? I think AWS did something like that recently, where you could actually upload VHDL files to the cloud or something, and they would reprogram them for you.
Yes, very good point, and that's indeed the case. I would have mentioned that later, but indeed, there are some cloud computing providers that actually have FPGAs publicly available. AWS is one of them. You can indeed just go there and get a virtual machine that has an FPGA or 8. And it can be even used in a model that you practically upload a VHDL file, kind of compile it, and then you run it or execute it on that cloud FPGA. There are also more abstracted services there, and there are also more cloud computing providers. I think that all the other ones are Chinese, like Huawei Clouds, Alibaba Clouds. Actually, all of these, including AWS, run the same Xilinx stack for cloud FPGAs. Azure not. Azure is something completely different. All right. One final note on FPGAs here is that, well, it's hardware design, and that means that to utilize them, you need hardware engineering knowledge. So you have to design, kind of a computer chip, but at least a piece of logic hardware. To alleviate some confusion, although probably you don't have any of these, although FPGAs have visible circuit boards, just as Raspberry Pis, for example, they have nothing to do with each other. Raspberries are, well, small computers. And FPGAs have nothing to do with microcontroller platforms like the Arduino or the NetDuino either. So to get back to our train of thought, what Hastlayer does is that it takes a computer program and creates an equivalent FPGA logic. And not just any computer program. I already spoiled it also in the on the talk's description that we are talking about .NET programs. Actually, what Hastlayer processes, if you are also familiar with parts of the .NET compilation pipeline, are the .NET DLLs, the intermediate language assembly files. And because of that, at least in theory, not just C# can be used as the original input language, but any .NET language, any language that compiles the .NET assemblies. And that includes Visual Basic and Managed C++, or even functional languages like F#, or even scripting languages like Python, PHP, or JavaScript. And all of these can be turned into FPGA logic. Alright, well, that's cool, I guess, but what's the point? Why are we doing this? And the reason is that FPGAs have some unique computing benefits, and we want to utilize that. So let's have a totally non-scientific, just very crude overview of the merits of different computing devices here. So let's compare CPUs that we all use every day, and GPUs that we most possibly also use every day, and FPGAs that we probably have never used. Well, let's talk about parallelism first, the chart on the left. So how many things can these devices compute in parallel? Now, CPUs in blue are kind of on the lower end here, because desktop CPU has 4, 8, maybe 12 cores, possibly twice as many logical cores, and the server CPU can have 32, 64 cores, but that's about it. Now a GPU, on the other hand, in orange, is on the other end of the scale here, because GPUs are highly parallel devices. They sometimes have thousands of little processing cores all running in parallel. Now FPGAs in gray are kind of in between here, because although there are no processing cores on an FPGA, so to say, though that's not entirely true, the level of parallelism you can achieve there is kind of in between, in the order of hundreds, sometimes thousands. Of course, all of these highly depend on the specific chip you are using and the specific application you want to run. Now, let's talk about the complexity of programs that you can run on these devices. The chart in the middle. Well, CPUs win here because if it's a program, you can run it on a CPU. Sometimes not directly, because, yeah, you need cross compilation, emulation, whatever. But in the end, most possibly you will be able to run it. With GPUs, it's different. The programming model is much more limited there. You can't just use any data structure. You can't just use any control structure. With FPGAs, it's kind of in between again. You can't really write a program for an FPGA, but if you take a program and convert it into an FPGA implementation with a high-level tool like Hastlayer, then what you can use in that program is kind of in between. Now, lastly, let's talk about power efficiency. So, how many things can these devices compute with 1 watt of power? The chart on the right. Well, CPUs and GPUs are roughly on the same level here, but FPGAs really shine. FPGAs are very power efficient devices. And the reason is that with an FPGA, you basically get an application specific processor. It will just do what you need it to do. It will just compute what your application needs to be computed. So there is no instruction set to handle, like with a CPU. There is no operating system to run, no noisy neighbors to handle. It will just do what you need it to do. And because of that, it can be very power efficient. And by the way, FPGAs are also generally low power devices, consuming a few watts of power. But there is a huge downside, and that is the ease of use, or rather the lack of it. Because programming a CPU is, well, easy enough. Programming a GPU is a bit harder, but you can manage. But utilizing an FPGA is something completely different. Because there you are not writing a program that will run on a processor, on kind of a processor, but you are designing a piece of hardware. You have to think in terms of wires and logic gates and clock cycles. It's very different. And if you are coming from a software developer background, it's also very hard. Well, as the name also suggests, hardware engineering is hard. But with high-level tools like Hastlayer, we intend to bring this complexity, this level of complexity down roughly on the CPU programming level. And I think we are already there mostly. So to summarize, what I aim for here is to get the benefits, the computing benefits of FPGAs for all of us software developers. Now, if you have an application that is highly parallelizable and is compute bound, so CPU bound, then with FPGAs and Hastlayer you can get a substantial performance increase. And at the same time, you can also get a higher power efficiency, so you can do more things faster with less power. If you think about applications that run on compute clusters with hundreds or thousands of servers, then power efficiency really matters as well. And with Hastlayer, this is all just programming as usual. Now, to give you a bit of an idea of where FPGAs are already used, here are a few examples. Not all of these have to do anything with Hastlayer, just FPGAs in general. AI and machine learning are where FPGAs are already used both for training and for execution. Image and video processing, as well as computer vision, are typical areas where the algorithms are highly parallelizable, thus quite suitable for FPGAs. Algorithmic trading or on stock exchanges, or better, high-frequency trading is something where FPGAs are widely used, because there you need sub-microsecond latency, and FPGAs sitting on a network can supply that. Data compression, although it's not completely compute bound, but there's a lot of I/O, are sometimes also suitable for FPGAs. I'm mentioning cryptography and cryptocurrencies together because the compute intensive task here is hashing, the hash functions, and FPGAs can be used for that as well. But not Bitcoin mining. That ship has sailed. FPGAs were at one point used to mine Bitcoin, just very briefly, but not anymore. They were surpassed by dedicated hardware. And due to their low power nature, FPGAs are commonly also used in embedded systems like robots or IoT devices as well. Okay, a lot of talk until now. Let's see a demo and let's see how you would work with Hastlayer. So now I'm opening Visual Studio, and what we see here, as the name also suggests, a parallel algorithm. This is an example, a kind of an exaggerated example of the class of algorithms that are suitable to be accelerated with Hastlayer. So it's not something from real life. And what this algorithm does is that it takes an input number and then starts tasks. Now probably not all of you are familiar with the taskbar library tasks in .NET. Its tasks are basically an abstraction over threads. So when you start a task here, then the .NET task scheduler will select a thread from the .NET thread pool and execute the task on the CPU. And how many such tasks will be run in parallel depend on the platform itself. So on my desktop machine here, I have an Intel Core i7 CPU with 4 physical, 8 logical cores. So the actual hardware level parallelism we will get is around 8. But we will start 280 tasks. Now these 280 tasks will still execute on these 8 logical cores on my machine. But once all of this is converted into hardware, then we will actually have 280 copies of these tasks. We will have a hardware level parallelism on the FPGA of 280, and that's where the performance benefit of FPGAs can come from. Now, what we do in these tasks here is quite simple. There is some conditional logic here, which is executed 10 million times, and then the result is returned back. Next, we wait for all of these tasks to finish, and once that happens, we sum together the results of the tasks, and this sum will be the output of the whole algorithm as well. Now, this is quite a simple code that we have here. There are also more complex examples that you can also check out on GitHub, and you can do a lot more in Hastlayer as well. But this here is just a simple example to convey the idea. And now let's also run this. I actually have an FPGA prepared here, so I'm showing it to the webcam so you can also see. This is the FPGA that I will use for this demonstration. It's a relatively low-end, low-cost, $300 US slow development board. So that means that it will be slow and it can't fit much logic. Bigger boards, for example, could fit more than 280 copies of that task. But still, let's see what happened. Sorry. What happened is that Hastlayer created the hardware implementation in the background and executed this algorithm on the FPGA 3 times. And as you can see, it took around 300 milliseconds each time. Well, actually, if you take a closer look, it took exactly the same amount of time, down to the 10,000th millisecond. And the reason is, again, that with FPGAs, you basically get a hardwired logic. There are no noisy neighbors. And because of that, the execution time will be deterministic as well. Now, on the hardware itself, it took about net 300 milliseconds, but if we also take the latency with the host PC into account, then it was just below 400 milliseconds. The difference here is the time that took for the data to go from my PC to the FPGA board and back. Now the difference here is quite big, and the reason is again that this is a slow FPGA port. It just has a USB, well, it has a USB and an Ethernet port, and we use the USB port here for data exchange, which only offers a quite slow virtual serial connection. But with bigger, faster FPGAs, of course, this latency would be smaller as well, for example, by using PCI Express. But even like this, it was much faster than the CPU, because on the CPU, this example took around 3 seconds. It's about 10 times more. The FPGA was about 10 times faster than the CPU. Now, of course, this wasn't a very scientific measurement either, because my machine is doing a lot of other things at the time. But even if it would be idle, and with repeated measurements, it would be just below 2 seconds to execute this. So still about 5 times slower than the FPGA. Now this should give you a bit of an idea of what's possible with Hastlayer and with FPGAs. There are a lot of other examples on GitHub that you can check out. We won't cover those now, but just one thing, because we have seen how an algorithm looks like that's implemented with Hastlayer as an FPGA, as a piece of FPGA hardware. But what we can see here now is the main class of this console application that I've created. And here we have how you would orchestrate Hastlayer. This is how you would plug Hastlayer into your existing application. And what we see here, well, there's a bit of configuration, not too interesting. What's interesting is this generate hardware method call here. This is where Hastlayer takes an assembly, a .NET assembly, and creates the hardware implementation of it. Now, actually, the hardware implementation is here. This is the code that Hastlayer generates. As you can see, it was created a few minutes ago when I've started the console application. What we see here is VHDL code. VHDL is a hardware description language. So this is basically the hardware code that Hastlayer creates. And it's quite, well, it looks a bit like a programming language, but it really isn't. It might look also complex. It's not that complex, but it's very long. It's tens of thousands of lines. Well, 70,000. And that is because of the lot of copies. Because what we see here is that there are some familiar names with parallel algorithm and run in this block that we have here. And this block, of course, has to do something with the task in our parallel algorithm sample. And actually what we see here are type declarations corresponding to the task. And if we take a closer look, if we can see that it has the index 0, and the same thing a few lines below has the index 1, and then the next one has the index 2. So you may have already guessed that this is where we have all the copies, and actually indeed if we scroll down here, we'll find all 280 copies of it, because here is the last one with index 279. And now these are here just the type declarations. The logic itself comes later, but here is where you can see that on the hardware we have those 280 little processing cores. The logic on the hardware, on the FPGA, is actually all running in parallel, not just on 4 or 8 cores, but on 280 cores. If you go back to the C# code,
is the code repeated 280 times as well then in that file?
Yes. Actually, in VHDL there will be other techniques for that as well. This was more straightforward to implement for the code generation. So if you scroll down, we will see 280 copies of everything here as well, in these 70,000 lines of code. And now if we go back to Visual Studio, one further thing that we see here is how we execute the hardware implementation, because that was how we generate the hardware implementation, and here is how we execute that. Remember that I told you that the hardware implementation is executed 3 times? Well, that happens here. And as you can see, the interesting thing is that there is nothing really interesting. You just call the run method. So this is the same run method that we see here in the Parallelism class. And the reason why this works is that because on this line, we take an instance of this Parallelism class and wrap it into a dynamic proxy. What this basically allows Hastlayer is to hijack method calls. So when you call the run method here, Hastlayer will take it over and transform the execution to the FPGA. It will push the data to the FPGA board, do the execution, wait for the data to come back, and return it back as a standard .NET object or value. So all of the FPGA communication and everything is handled by Hastlayer seamlessly. And this is another case where we come from affected the design decision, because again we want to provide a tool to software developers, and as a software developer I don't really want to care about the FPGA side. I just want to execute my logic. I just want to run my program, and here we offer a way to do that with as little friction as possible. And by the way, this also allows you to offer optional hardware acceleration to your program or for your program, because what you have written in your Hastlayer compatible code is just .NET. You can just run it as standard .NET code. You can also debug it as standard .NET code. But if there is a compatible FPGA board present, then Hastlayer will detect it, and these method calls will be transformed onto the FPGA. If there is no FPGA present, then these method calls will just execute as standard software. All right, let's get back to the slide deck, and let's wrap this up. Now, what's next for Hastlayer? Because this is where the project is, but we are not stopping here, of course. For example, we are doing some field testing with real life examples of to test Hastlayer. We have also engaged into a partnership with the Wigner Research Center for Physics, which is part of the Hungarian Academy of Sciences. Some pretty smart guys there, mostly physicists. And what we want to see with them is how Hastlayer can help scientific computations. We actually have an example among the examples that are also on GitHub, which is an algorithm we got from them. It's more power efficient than on a CPU, but not yet faster. And the reason is also that our FPGA is too small currently to fit enough parallel executors of that more complex program. We are also working on floating point support. So floating point is something that FPGAs generally struggle with. What we have done is not support for the standard .NET float and double types, but a custom number type called POSIT. POSIT was invented by a mathematician called Dr. John Gustafson, and it promises to be even better than standard doubles and floats. And we have an implementation of that. It's not complete yet, but it works. And it also shows a quite interesting example of Hastlayer, because with Hastlayer you can also create a .NET library with your own custom number type, just as we have done with POSIT, and in 10 seconds you can have hardware support for that, hardware acceleration. Because what Hastlayer basically created for our POSIT.NET library is kind of a POSIT processor. So I think quite exciting. We are also working on making Hastlayer high performance computing ready. As mentioned, this slow development board that we have here is kind of a bottleneck, but we are working on supporting much bigger, much faster cloud FPGAs. And FPGAs are coming into every data center out there, it seems. As we have talked about, Amazon Cloud already has FPGAs, Azure already has FPGAs. One thing we haven't talked about is Intel, because probably you have heard that Intel is also an FPGA manufacturer, because as of 2 years ago they acquired the then second largest FPGA manufacturer called Altera. And what they are working on is, among others, bringing together their processors, their CPUs with FPGAs, particularly packaging together a Xeon server CPU with an FPGA. And if you think about that, that's quite a logical step, because CPUs can't really be made much faster anymore. We have reached the maximum clock speeds a long time ago, and nowadays we are reaching physical limits on how many transistors can fit on a chip. But with FPGAs, you can cheat the system, because if you put an FPGA core into your CPU, then basically you have put in an application-specific CPU core, and with that you can make your CPU execute programs faster without actually making the CPU run faster. So we'll see what Intel will bring. Now, if you like this, and I really hope you did, go check out the SDK. It's up on GitHub. You can use Hastlayer for free. And be ready, because it seems that FPGAs are coming. If you can remember, maybe 5-8 years ago, GPU programming was quite different as well. Of course, video game developers did it, but if you wanted to use GPUs for general purpose computing, that was quite cumbersome. But nowadays, if you are a software developer, you can basically program a GPU as well. With FPGAs, we are going through the same shift. FPGAs are still a bit of a curiosity, but not quite shortly, I think, we will have just another computing device in the case of FPGAs to choose from for all of us software developers. So thank you for your attention. If you have a cool use case for Hastlayer, let me know in an email. I would love to hear about that. If you want to check out some more details, Hastlayer.com has everything. Again, the SDK is up on GitHub. And if you are curious about the curious people behind Hastlayer at Lombic, then check out lombic.com. And now we can have a bit of Q&A, a bit of discussion, if you are up to it.
So Sean's saying, can the code in the FPGA react to external values, like from a transducer or a thermistor or some other voltage level? And how would you test that in Visual Studio?
Yeah, very good question. I can answer the how do you test it in Visual Studio easily, because you don't, because this is not supported. The reason is that the supported model of using Hastlayer is that you have a piece of compute-intensive logic that you kind of outsource onto the FPGA, and then you call that logic. Then you execute that logic, and that's it. So at the time, we don't have anything to support using the FPGA as an embedded hardware independently of a computer, of a host PC. That being said, I would guess from this question that Sean, you are also closer to hardware development, right?
Sean has to type. Sean's actually a software guy.
The software guy. Okay. Then just a software guy with some interest in lower level hardware development.
Yeah, he's a smart software guy.
Well, just one note here then. All that being said, you can also very cool. So that being said, although the basic model that we support out of the box and that is very easy to use is this call into the FPGA implementation thing, but the hardware implementation that Hastlayer generates has a very simple interface. Now, if you are familiar with VHDL, you will see from a first glance that indeed this is very simple. If you are not a VHDL developer, you will also see that it's quite simple, because we have a few Boolean ports on the interface of this hardware component, a few integer ports, a few single logic ports that are basically 0 or 1, and we have 2 data buses. So that's really a very simple interface. And what this allows you is that you can generate this logic with Hastlayer, and if you have an existing hardware design, or you create a hardware design that should be for an embedded system, then you can plug this Hastlayer component into that hardware design quite easily, since the interface is simple. Now, we don't explicitly support that. I mean, we haven't created samples for that, for example, but it's possible. There is nothing preventing you from it. There is nothing else happening in the background than what's apparent from the interface. And this way you could use Hastlayer in a more traditional high-level synthesis tool like Wave, and even hook it up with thermal sensors, even, for example, on the data in port.
So, does this work with Visual Studio on the Mac? Do you know? Have you tried it?
We haven't tried it, so I don't know.
Okay.
There would be issues, I think, because Hastlayer currently uses the full standard .NET framework. We haven't tried Mono, so most possibly this is just Windows only. That being said, .NET Core support, or rather migrating the .NET Core, is on our roadmap, just not a top priority, and that would be basically multi-platform. Yeah.
So what's the are there a specific set of boards that you all support, or do you have is there I don't know, is there a standard API that all these FPGAs support, or how do you work with different boards?
Mm-hmm. The second part of the question also kind of foreshadows my reply to the first part. We support only a single board right now, and the reason is also because there is no such kind of common API. Well, FPGA ports and FPGA chips are similar, but to utilize the different capabilities of them, we basically have to support all of them individually. Now, we have chosen a path where we only support this particular development board, which was fairly easy to support, and by that I mean that we needed like 8 months of development to have the framework there. But we won't support at the time any other boards for local development. But as mentioned, what we are working on is support for cloud FPGAs. That being said, this is a Xilinx board made by the FPGA manufacturer Xilinx. So if you want to use another Xilinx board that has at least as much resources as this one and has a UART port, possibly via USB, then it should be fairly easy to port it over.
Did you have to configure that Xilinx to support this, or are you basically injecting that hardware accelerated code straight in over JTAG, or I guess that would be described in your SDK, right?
It's actually described in the hardware framework repository, which is also up on GitHub. But since you ask about it, let me also show you the block design. The short answer is that we inject, we build everything ourselves, and that's then programmed onto the FPGA. And what we see here is, is a high-level overview of the design that's on the FPGA, including the generated component that we plug into this here, this Hast IP. And as you can see, basically we also have a microblaze software processor in the middle. This whole framework that we have on the FPGA is then indeed configured via JTAG. There is no prior configuration needed, no, I don't know, specific jumper configuration or anything like that.
So every time you run the .NET application, you've precompiled the VHD and you just pass that into the FPGA that's communicating with that microblaze build that you're showing there, or is that all built and loaded into the FPGA every time?
You just need to do that once. So until you power off the FPGA, it will keep the configuration. Because by default we don't put the configuration onto the flash, it just goes directly to the FPGA. And secondly, this hardware implementation that Hasler generates, the VHDL code, is also cached. It isn't cached now because it's deliberately switched off for the sake of the demonstration. But if you would use Hastlayer in a real-world scenario, repeated executions don't have a performance penalty. And by the way, you don't have to completely restart Hastlayer either. So what we have here, starting here, is how you start Hastlayer. But inside that, or once Hastlayer is running, you can have as many hardware executions as you wish.
Do your researchers use what I'm understanding is that part of this is the C# to VHDL code emission, and then the second part is basically hosting it in the .NET application. Do your researchers use the basically C# to VHDL translator kind of by itself for research, or is it all tied together very tightly? I guess.
Yeah, that's also a good question. First of all, it's intermediate language to VHDL. Okay. So any compiled .NET application can be processed here. As long as the intermediate language code won't be too alien, but usually the different compilers still produce pretty similar results with the same code structure. What you ask about, if I understood correctly, is also about a bit of high-level synthesis use case. And that's what I mentioned, that you can do that, but we don't support it specifically. So that's very good. Write your algorithm in Hastlayer or in .NET, generate the VHDL with Hastlayer, and then don't use anything else, but rather basically plug this hardware component with this mentioned fairly simple interface into another hardware implementation.
Right.
I would be happy to see that in action, but we haven't done anything to support it specifically.
Okay. But that VHD that you emit, that is available for use if because we do embedded systems and there have been technologies that kind of do translations like Impulse C that will take some C language and kind of convert it to parallel. But this is very cool in that you can run it straight in a .NET host.
I would say that as a generic high-level synthesis tool, If you are looking for embedded use cases, Hastlayer is probably not the best choice because it was not designed with that in mind. Really, the aim here was to it's not even about hardware design and about FPGAs, but rather to give .NET developers a way to increase the performance and lower the power consumption of their applications. So to open up high performance computing scenarios that otherwise wouldn't be feasible. So in that way, we also don't optimize in the same areas like high-level synthesis tools. How you use Hastlayer is also very different. Because as you have seen, you pretty much have to know nothing about the hardware side. You don't tell Hastlayer that, okay, optimize this in such a way for the hardware like you also do in high-level synthesis tools. And because of that, we haven't measured, but I'm very sure that the code that Hastlayer generates will be worse performance-wise than that of the high-level synthesis tools of, for example, Xilinx. But we are aiming for the development experience / performance sweet spot. But nevertheless, if you use .NET anyway, and you develop embedded systems anyway, probably it's worth a quick test. Because, well, you just write some C# code, 2 seconds later you have the VHDL, the interface is there. This is not documented, I think. Yeah, I don't think we have documented it outside. It's quite self-evident, though. The parts that aren't, we can tell you if you are interested.
Okay.
Right, Brett has some questions. Do you plan on providing building blocks for the physical interface? Oh, yeah, SPI and IC. Yeah, those are also very good questions, and also something that we have on the far end of our roadmap, but not right now. For now. For now, the primary intent is not really just to allow you to use the USB interface. And by the way, we also have an Ethernet interface. That's a bit faster, and you can also hook up multiple FPGA ports to a network switch, for example, and Hastlayer will be able to discover them. But the primary intent is not really to constrain you to use the USB port, but rather to handle everything on the hardware side and on the software side, so you don't have to care about that. and that includes the communication as well. We don't have anything on the hardware side to let you connect the hardware implementation with any other hardware components, like any other ports on the board. Or on this board, for example, we have switches and LEDs and the display and the VGA port. Those are not supported at all. And also, this is also having to do with the model, the computational model that I've mentioned before, is that it's for software developers to increase performance and lower power consumption. There is this magic tool in my computer that does this, but I don't care about that more. That's the basic idea. And again, that being said, further steps, further down the road, we definitely want to support hardware level building blocks as well. Our first ideas aren't about ports specifically, but about IP cores. So, for example, there are video encoding hardware components that you can purchase, or sometimes are even bundled freely with development tools. And we would like to make them available somehow. So you can somehow interact with that video encoder IP core, so you don't have to implement video encoding in .NET, nor do you have to do anything else. All right, those are also very good questions, and I can understand that some of you are coming or looking at a bit from the hardware side as well, more than an average software developer would do.
So now on the translation of intermediate language to VHDL, what all is supported in that? Like, can you make virtual function calls in that, or what all is supported?
That's also a very, very good question. First of all, what we have here is just a simple example. Much more is supported, but there are limitations. Limitations because we didn't have time to support everything, and limitations because of the different computing models. We have extensive documentation about that. There is this working with Hasler documentation page, which is also linked on GitHub, so you don't have to open the file, but you can browse it online. And here it's documented what is supported and what is not supported. If you try to use something that is not supported, then you will get an exception, so it will be very apparent. To give you a basic idea, most of the fundamental constructs of .NET are supported. You can write object-oriented code, but where there are limitations enforced are all around, well, let's say that would be dynamic behavior with memory interfacing, or where a garbage collector would be needed. And the reason is because the logic will be wired in. So, for example, you can create arrays, but those arrays have to the size of the arrays needs to be determined in compile time. Hastlayer can figure out with constant substitution, so you don't have to have actually a constant in the array creation expression, but it has to be determinable in compile time. And that is also because on the hardware that array will be wired in, most possibly as a piece of or several pieces of distributed RAM. And well, we need to know the size of that. Basically, all the limitations are similar that we won't be able to work around. There are some other limitations that we didn't have time yet.
Is there any support for calling back to the application in the middle of processing?
There is no support. That's also for that. That's also a very good question. The programming model is that you call the hardware implementation and that returns some result back, and that's it. Back and forth. We thought about having some other model, potentially with some streaming functionality or stream-like processing, but at the time we haven't done anything. And for now, this works fairly well. It's usable. It's not supporting everything, but it's good enough for now. All right, those were some very good questions. Great conversation. Thank you.
As far as the efficiency goes, if you compare the FPGA to like an ASIC, as far as like computations or power, what's the difference? How's that compare? Because you did the CPU and GPU.
If we go to this chart, ASICs would be kind of an exaggerated version of FPGAs here. So, but with a huge drawback, and let me touch on that later. So, so ASICs, or for those of you who probably haven't or don't know this, application-specific integrated circuit. So basically hardwired chips, hardwired hardware, and not dynamically reconfigure FPGAs. They have the benefits that they can be even more power efficient than FPGAs. They can have denser logic so they can have more logic per area, so they can have a higher degree of parallelism. But the complexity of, well, again, programs with codes that you can run there is lower because you most of the high-level synthesis tools that you would be able to use, including Hastlayer, are not available for that. And the biggest drawback here is that the costs of ASIC development is, well, at least 2 or even 3 orders of magnitude higher than FPGA development. So they say that if you want to begin ASIC development, you need well, a couple of years and a couple $1 million. As of with FPGAs, you can hash out something fairly quickly, although FPGA development itself is 1 or 2 orders of magnitude slower and more expensive than programming. But with FPGAs, you can still roll out something fairly quickly. You can buy an FPGA for maybe a couple $1,000s, but that's it. With ASICs, the development is much slower, much more expensive. You have to be very careful because you can't change an ASIC. And then finally, when you have the design, you have to manufacture it, which is only feasible if you want to sell tens of thousands of units.
Do certain companies use like FPGAs to basically do like a proof of concept for an ASIC?
That's actually one of the foremost usages of FPGAs. And originally, if I'm not mistaken, FPGAs were created precisely for that task. Now they are much more, but originally that was the case. So, for example, a chip manufacturer like Intel, they have enormous FPGAs and a cluster of enormous FPGAs to kind of emulate as a recent CPU, for example.
Okay, that's cool. So it sounds like, I mean, you're able to use this FPGA kind of like as a coprocessor, essentially, that you could reprogram over and over again to run specific codes.
That's exactly right. With an FPGA, you basically get an accelerator card, just as a GPU. Just it's a different kind of one, a dynamic one. And by the way, touching on the topic of ASICs, in theory, you could also take VHDL code that's compatible with an FPGA and create a physical chip of it. Well, not directly because there are changes needed, but in theory, this would also work. So in theory, you could also take the logic generated with Hastlayer and go to a chip foundry and get a chip manufactured. Then again, you will need a lot of other things for the framework on the chip side to wrap around this hardware component that Hastlayer generates, but that would be also possible. I wouldn't recommend that, by the way, but of course, anybody who would want to create an ASIC would know that pretty soon. Okay, then probably this was the last question. So again, very good questions. I'm glad that we had this meeting.
Well, thank you so much for coming. We really appreciate it. This has been a great presentation.
I'm very happy to hear that. The recording hopefully will be all right. So once it's processed, I will share it with you, Jonathan, and you will be able to publish it if you wish.
Sounds great.
All right, great. Thank you, everyone.
Thank you.
Thank you.
Bye-bye.